Hi, Dr. Anthony Revis here with Watch Me Do It. So I want you to watch me do it with this chemical bonding, hybridization, molecular geometry, VSEPR structures. So it's that type of concept we're going to work through a couple of things. And we're going to do it from this one single chart here, okay? So we're going to write all over this. It's probably get really messy. So hang in there. Now what we're going to look at is the total valence electrons here. And we'll just do some of this chart and we'll leave the rest to you. We might draw some Lewis structures. Steric number is going to be pretty important to what we want to make sure you see. ABE format, VSEPR form. And when we say the VSEPR form, we'll be talking about whether it's tetrahedral, linear, those types of things, the hybridization. Okay. You want to be aware that there are different terms of use. For example, you hear terms like domain, name, used, and you'll also hear things like electronic geometry used to describe some of these. So you want to be aware of that depending on whose text you use or where you read it, you might see something different. So what you'll know how to do this when you see the answers here. Okay, so just keep that in mind. All right, so here we go. So we may do valence electrons. Why not? Let's just do them. When it comes to the valence electrons, you can really go to the periodic table and get this over really quickly, right? You have hydrogen and you have two of them, right? And where it's located. So hydrogen um, by itself has one valence electron. So that's two of those hydrogens times one. That's going to give you two. And we have oxygen here, which is on the periodic table group 16. So that's six. So total valence electrons used to make this is eight. So that's what you do there. So you just calculate. Okay, simple math. Don't do anything deeper than that. The Lewis structure happens to be bent. We'll draw that here for you. Probably move on from drawing so many of these. But we'll just show it to you there. So we have that. And we just said that it's bent, right? Its VSEPR form is what we call bent or angular. And I use the word VSEPR form for this, or I should perhaps say VSEPR geometry. Okay, it's bent here and it's angular. So you'll hear VSEPR geometry used here. Okay, and you'll hear other terms used to describe these. So just be aware of it. But this is basically your geometry. And I just want to use the term VSEPR to reinforce that to you. And then we have what's called the ABE domain format name here. And we name this by saying the central atom is basically A. And then we look to see what we have around it based on the Lewis structure. And we have two atoms around it. So that's going to be your B, two around it. And we have two sets of lone pairs. So E is going to be electrons, your lone pair. You have two sets of lone pair electrons. The hybridization here around the oxygen, it has four geometrical spaces that have species in them. Two of them are loaded with atoms and two with electrons. So two of your electronic spaces are covered by lone pairs and two by atoms. So that's a sp3. And here's how you know it. You have one in the S, you have three in the P's. That equals four. That's the number of spaces. Locations. So you have these geometrical locations where you can put either atoms or electrons, and that comes out to be sp3. So just following through, we'll do a couple more here. Carbon dioxide, we have four valence electrons from carbon and 2 times 6 from oxygen. And it's a little prouder here, but that's okay. And so whatever that turns out to be, you just calculate those there. And so that's 12 plus 4, 16 total. So make sure we do the right arithmetic here. Okay. So that's total valence electron used here. In this particular case, we get a linear geometry. That's what its Lewis structure looks like. So the geometry, VSEPR geometry, and this should be really say geometry here, okay? So keep that in mind. That's what we're really talking about here, okay? And this is linear. Draw us a little linear here. And so this is linear. Oh, by the way, the steric number is what we're talking about when we're saying the sp3. That's 4 here. We have 4 groups around there. Around this one, we have 2 steric regions that are occupied here. 2 bonding regions are occupied here. And so this is going to be A for the central atom. B, I have 2 things around that central atom with no electrons. And the hybridization, I have 2 things. I have to count for S, count for 2, so it's sp, hybridization around the carbon. Count these electrons up, you have 15 plus 3, 18 total valence electrons. Here, geometry looks like this, kicked off of not a very good, and so not a very good tetrahedral sp3. So its base geometry would be tetrahedral. However, because these electrons are pushing these hydrogens down, this is called trigonal, meaning 3 groups, pyramidal. So trigonal, I'll write out here. Okay, middle. I am not writing too well right now, am I? That's a lot better. I told you, this is watch me do it. You see it all live. Around this, we have 4 steric groups around it, 1, 2, 3 hydrogens alone pair. The geometry A for the central atom. It's always A. B, how many groups they have around it? On the elements, 3. And how many lone pairs? 1. Get it? Let's just go on down here to BF3. BF3 is going to be looking like this because there are no lone pairs on the boron on the central atom. Therefore, its hybridization is going to be sp2, 2, 3, 3 things around it. It's going to have an AB3 with no E on it. And this is just going to be called trigonal planar. Okay, and so that's how we do these, and we go through and we can do any of the others the same way. Here, this is a B to show you AB 1, 2, 3, 4, AB 4. Doesn't matter what the groups are, you just put them around it. And this one's a little bit more tricky here. So we have all 5 groups around it. So we got 1. Let's draw it out here. Sorry. B, and we have 5. 1, 2. See, we'll draw like this wedge. 2, 3, 4, and 5. And so BR. No lone pairs left on that. So this is going to be a B5 is what we have here. And then you could perhaps do the others. This is going to be a sp3 hybridized. This is going to be a sp3. We run out at 3 as high as we can go, but we have to count 5 things, 1, 2, 3, 4. So it's going to be a D there. And so here the hybridization is going to be sp3. How many? That's 4. So you're going to have a D2. You get it? All right. And then you have the other geometries, which I'm sure you could play with and figure out. Steric groups around here is only 3, 4, 5, etc. Okay. Got it? So that's how we look at the molecular geometry when we do these VSEPR type geometry problems. And keep in mind, the VSEPR form is really your VSEPR geometry is what you really want to look at there. Okay, it's called geometry. All right. That's how we do it.